Right, sorry, we are learning about the preparation of benzene from alkenes. If you have n-hexane form, we can get benzene out of these reagents. And if you already have a cyclic hexane case, hexene, or diene, all of them will convert into benzene in the presence of sulfur, selenium, or platinum and heat. Alkynes, if you use red hot copper tube or red hot iron tube, and I take 3 moles of alkyne here, so that will convert into benzene as well. Okay. Another way you can notice that in case if you have CH3C triple bond CH, and if I take 3 moles of it, then it will convert into benzene, but having 3 methyl groups at meta to each other. And this product is called as mesitylene. Okay. Idea is the same. We need to have red hot iron tube or red hot copper tube. Okay. Second. Red hot iron tube or red hot copper tube. Next. In case instead of using red hot copper tube, I use nickel complexes or cobalt complexes, then 4 moles of it will give you cyclooctatetraene, which is this form. Okay, alternative double bonds. And if you recall from GOC, we learned this part that cyclooctatetraene is a non-planar tub-shaped compound, COT, cyclooctatetraene, and it is non-aromatic in nature. Na means non-aromatic. Okay, next. If we use phenols and react that with zinc, zinc will give away electrons and make hydrogen to come back here and takes the oxygen along with it. That's how benzene is being formed. Halobenzene's first reaction with magnesium makes a Grignard's reagent. You'll get minus charge here and MgCl plus charge here. And that when you treat with H3O plus, that means you will get hydrogen here, leading towards benzene form, and magnesium becomes OH and Cl here. Next, from carboxylic acid. If you have COONA, carboxylic acid, first with NaOH and CO, remember this, we learned in hydrocarbons, soda lime decarboxylation. Soda lime decarboxylation is going to make this as minus first carbon anion will form, and that treated with water will convert into benzene form here. So, and the carbon dioxide which is removed will be as a part of NaOH as N2CO3. Next, benzaldehyde. If mild oxidizing agent is used, any mild oxidizing agent is used, it will convert into an acid part, and that acid when you react with again NaOH in the presence of CaO, which is SLDC, will convert back into benzene form. Same is the case with cyanide. Cyanides on hydrolysis will always give you acids. Cyanides are unstable form in aqueous solution or acidic solution. And again, using SLDC, you can convert this into benzene form. Okay. Next, aniline. Aniline, this is aniline. Aniline, when you treat with HNO2, okay, HNO2 is nitrous acid. Okay, nitrous acid. With nitrous acid, it will convert itself into H here and N2 gas is released. Okay. Basically, it forms something called diazonium salt. You can see the mechanism here. Usually, an HNO2 is unstable acid. Okay. It is only been prepared just before the reaction. Okay. Because you cannot keep it for a long time. So just before the reaction, what we do, we take NaNO2, add it with dilute HCl. So that will convert into NaCl plus HNO2. This HNO2 in acidic medium, because you're still keeping it in dilute HCl, will eliminate this water out and create a electrophile NO. And this electrophile will be attacked by the lone pair present on the nitrogen, converting that into, N2 plus. And this N2 plus is what we call it as benzene diazonium salt. Okay. Now this benzene diazonium salt, when you treat with H3PO2, that on hydrolysis will give you benzene, H3PO3, N2 and HCl. So this is the way we can get benzene. So wherever you see aniline with HNO2, understand that this is a reaction towards benzene. Okay. Next, if a reaction is given from nitrobenzene, see, nitrobenzene can be reduced using tin or zinc or iron in the presence of HCl to convert into aniline. And aniline further converts into disonium salt, N2 plus, and disonium salt in the presence of H3PO2 will give away hydrogen, and that's how you will get benzene. Okay, and this will become H3PO2 will get oxidized to H3PO3. Don't worry about the mechanism part here, it's not essential in the last step. You just need to remember that disonium salt will give you benzene at this point. Lastly, in case if you have sulfonic acid in the presence of dilute HCl, dilute H plus or H plus and steam, it will get something called desulfonated, which means benzene will come here, SO3 will be out. And if you increase the concentration of H2SO4, the reverse reaction will happen. Dilute solutions or heat will favor forward. Concentrated H2SO4 favors backward reaction. Okay. These are the preparation reactions for benzene, everybody. Okay. So quickly go through these reactions. Once again, check all of you 1 to 9 reactions first. What are factors you need to remember about benzene? Check. Benzene and benzenoid are very weak pi electron cloud because of high resonance energy and aromaticity. The term weak pi electron cloud refers to the availability of pi cloud. Okay, that this pi bond is not as easily available as that of alkenes. You know that alkenes are extremely reactive towards electrophilic addition. We did this in alkenes, that wherever there is a pi bond, it will go for Markovnikov addition and so on. The same doesn't happen that easily on benzene because the pi bond is extremely involved in aromaticity. So pi electron cloud is not enough to attract electrophile and show electrophilic addition reactions as that of alkenes. Benzene and benzenoid forms. Benzenoid means which have benzene rings like naphthalene, phenanthrene, biphenyl and so on. They do not usually show electrophilic addition. Hence, if they do not show electrophilic addition, they do not decolorize Bayer's reagent or they do not react with bromine water easily. Okay. Next, benzene and benzenoid forms show what type of reactions then? They will show electrophilic substitution, nucleophilic substitution, and few radical substitution. Electrophilic, nucleophilic, and few radical substitution. Got it? See, when I discuss about nucleophilic substitutions, I'll discuss every part of nucleophilic substitution, which is there for your reaction mechanism course also, which is SN1, SN2, and so on. So don't worry. When we come to part 2, I'll discuss all of the type of substitutions. Now, this is very unique. This does not require any background. EAS only observed in benzene case. So now check out. Electrophilic aromatic substitution. How does that happen? So we learned that the pi electron cloud is weak to attract the electrophile. However, in the presence of a strong acid, instead of addition, substitution will definitely take place. Okay. Now, how does that substitution happen? See, this is a overall reaction. A benzene will try to extract this electrophile, which may be connected with the nucleophile earlier, something like Br and Cl are present. To remove this chlorine, we require a Lewis acid. So this Lewis acid will take away chloride and puts back bromine plus charge. And that's where benzene can attack bromine plus charge and get bromobenzene. Stepwise, how does it happen? The step 0 means creation of an electrophile first. So first is about creation of electrophile. So how are we doing that? Suppose if you have Br and Cl, as per this question, let me write down electrophile and nucleophile here. Electrophile and nucleophile are connected here. And then you have a Lewis acid. Let's say AlCl3 is one Lewis acid which has an empty orbital. So then the lone pair present on the nucleophile, it will attack on AlCl3. That will make it as electrophile, and AlCl3 with nucleophile goes and makes it as a negative charge overall. This is what you will get. So the first, I mean, the zero step is always about generation of electrophile. Once you generate the electrophile, now benzene, which has pi bonds on it, will try to take this electrophile onto it momentarily. Okay. Now by which, what would happen? Electrophile will come here and positive charge will come here because the pi bond got shifted onto one side. Correct? So you will get this intermediate which has a loss of aromaticity. There is no aromaticity now. Loss of aromaticity. So if there is any loss of aromaticity, the ability to push in this direction will be very slow. That's why this is the rate determining step or the slow step of the reaction. Okay. Once you get this step here, you know this particular intermediate which is forming here with a positive charge and hydrogen present here. In fact, hydrogen is present on all the carbons. I'm just showing at one position. Okay. And if you notice the second step here, clear? So what you will find here is that nucleophile here with AlCl3, the lone pair present here with this negative charge which is there, that will extract the proton from here and try to push the electrons to retain back the aromaticity. So you'll get double bond, double bond, double bond with electrophile here, and nucleophile will take that hydrogen and disconnect from AlCl3. So AlCl3 overall is acting like a catalyst. It was initially involved, now it has come out. Now what happened? This is the gain of aromaticity. So gain of aromaticity. So because it is gaining the aromaticity back, so it will be a fast step. Okay. So this is how the reaction proceeds, everybody. So three steps literally. One is step 0, 1, 2. Okay. Now if you may have checked properly here, this is an intermediate. So if this intermediate is more stable, then you can say the reaction will be more effective in the forward direction. And that's what you can notice through graph also, that if this benzene is attacked by electrophile here, it might go through a large amount of activation energy to reach this intermediate. And from this intermediate, it will eventually convert into this substituted compound. So rate of intermediate mainly depends upon stability of carbocation intermediate, carbocation intermediate, carbocation intermediate. Okay. And the rate can be written as some constant into benzene concentration multiplied by electrophile concentration power 1, right? Because this is the slow step, rate law can be written always for the slow step, and in the slow step you have two reactants involved, so therefore power 1 and power 1 here. Okay. Order of the reaction is 1 plus 1, which is 2. Overall reaction molecularity is 2 because there are two molecules involved here. All okay, everybody? So you can see in general, electrophilic aromatic substitution does not show kinetic isotopic effect, which means kinetic isotopic effect is the idea that you are removing hydrogen during the rate determining step from the molecule. If you are removing hydrogen during the rate determining step, then we say we have kinetic isotopic effect. But since hydrogen's removal is in the third step, or what we call it as the second step here, which is not a rate determining step, hence it does not usually show kinetic isotopic effect. Okay. Therefore, rate of benzene will be same as that of rate of benzene with all deuteriums, of rate of benzene with all tritiums. Okay. Clear? So all three will be same for electrophilic aromatic substitution. Clear? So please go through it once quickly. Check out EAS, everybody. I'll give it a minute's time, then we'll go ahead. Right. See, in case of iodination, that means substitution of iodine, substitution of SO3H, then kinetic isotopic effect is observed, which is in case nitration, alkylation, halogenation, all these cases, you would not see much difference in the rate. But if it is iodination and sulfonation, you will see benzene will have stronger rate than deuterium form than tritium form. Okay. And you can notice that if this is the activation energy, first activation energy and second activation energy, you notice that in the second activation energy is higher than the first activation energy. That's why the second step, although it is retaining aromaticity, let me show you that. Suppose when you react this with I plus and you are expecting that an intermediate must be formed here where iodine, hydrogen with plus charge, double bond is present. This is a loss of aromaticity. And we know that this is supposed to be the rate determining step, but the second step where you have iodine and hydrogen, uh, with this case plus, we have B minus, right? This getting into iodine form here like this with BH here. This would be rate determining step. Okay. Why? Reason being this base is very weak base. In this case, the base is actually I minus. I minus extracting H plus is extremely difficult. And that makes this reaction slow despite the fact it is actually giving aromaticity. That's why the second reaction is going to take a longer time compared to that of first reaction. And that's the reason, because you are removing hydrogen from the second equation, which is the rate determining step. Now you'll have a high effect on the isotopic nature. So if it, instead of hydrogen, if it is a deuterium, it requires a much longer time. Okay. So I guess this part is clear, everybody. So only in these two cases that happens better. Rest all the cases of substitution, you will not see any type of change in terms of rate. Next. Now let's notice EA's reactions one by one, because the overall mechanism is the same in all the cases. There is not much difference in the mechanism. Check out. The first is halogenation, basic halogenation, where you have benzene plus X2. This X2 can be chlorine and bromine. Okay. In the presence of a Lewis acid like AlCl3, FeCl3, or basic iron also, they all will act like Lewis acids. It can give you halobenzene. Okay. To put you through the zeroth step, this is what it happens. XX plus AlCl3, okay, will make this into a weaker bond. So XX becomes a weaker bond here, and AlCl3 will make it a stronger bond. So this will become delta minus and delta plus. Okay. And this is the electrophile. 1 second. Okay. So you can see this particular halogen will be the electrophilic site for it. Hence, if you have a benzene group here like this, plus X, X, sorry. See, I could write completely dissociated halogen, or I can write it in this way also, minus and plus also, like this. So here, as the pi bond attacks here, this bond will break towards uh, aluminium here. So therefore, you will start gaining this halogen at this position. X will be here, positive charge will be here, and AlCl3, sorry, AlCl4 minus will happen. Okay. Now this is the intermediate which is formed. Got it? This is the intermediate which is formed. We have chlorine and hydrogen with a plus charge. And that when you react with AlCl4 minus, this Cl will take away, the Cl from here will take away H plus, and gets this into aromatic form and converts into HCl and AlCl3. Now notice one thing, everybody. The intermediate which is forming here, correct? Let us talk about that for a minute. See, we have a chlorine here and plus charge here. And of course, this plus charge will keep undergoing resonance. So it will get a positive charge here, double bond, and chlorine. And the positive charge will keep resonating at this position also, positive, positive, and chlorine. And okay. So if you notice, chlorine is here, and if you notice the pi bond here, that is moving all the way from here to here like this. Okay. And that positive charge is moving across this position, and this position. Okay. Here. Now, this intermediate, what you got here is basically a hybrid form. And the hybrid form, right, stability of this hybrid form is what you are supposed to check for the rate of reaction. This is called as arenium carbocation. Okay, this is called arenium carbocation or valent carbocation. Got it? Okay, or sigma complex. Sigma complex. All of these are alternative names for this intermediate. Okay, so stability of this complex, stability of valent complex, valent complex is, higher the stability, then rate of the reaction will also be higher. Okay, clear everybody? In all the electrophilic aromatic substitutions, you will always get something called an arenium complex, valent complex, or a sigma complex. Now, this stability of this complex is what decides how faster the reaction would happen. Okay. Now, if you notice when you do iodination, correct? The problem with the iodination is carbon hydrogen bond is not very strong. That is, first iodine will come here. That carbon iodine bond which is there, it is not very strong. And from there, to get into the aromatic form here, this will be extremely challenging because it will create HI. And I2 bond is relatively stronger than Ci bond. So what would happen? The reaction will be again reverse. Correct? That is the reason why this reaction becomes a slow step or the rate determining step in this case. Sorry. Play with her. See, what happens is the HI which is forming will always push this reaction backwards. So what we can do, okay, using using Lee Chatelier's principle, okay, if HI is removed, if HI is removed, reaction moves forward, correct? Now to push the reaction more in the forward direction, what we can do, whatever the HI which is forming, right, that can be removed out by using some oxidizing agent, mild oxidizing agent, like HiO3, HgO, HNO3. Okay, what will they do? See, for example, if I have HiO3 and I treat this with HI, both will undergo reaction to form H2 plus I2. Okay, now it is an advantage in both ends. One, HI concentration is decreasing. Second, I2 concentration is increasing. Even I2 concentration increase will make the reaction to go in the forward direction. That's why if you convert the HI into I2, it is going to be very advantageous for this reaction to make it in the forward direction. Okay. Of course, in iodination, the kinetic isotopic effect is observed. And if you want to avoid this entire idea that you have to take oxidizing agent and all, you can directly take ICl, which is interhalogens, like ICl, IBr if you take, then there is no problem here. It is direct reaction. If you take AlCl3, first AlCl4 minus will form, I plus will be developed, benzene will attack on I plus, you will get iodobenzene here. In such case, there is no problem. Second thing, X2 and water, that is HOX, can be effectively used for halogenation of benzene ring as well. That is, suppose if you have a benzene here, correct, and treat this with X2 and water, that is X2 plus H2O. Now, X2 and water relatively have these bonds here. We learned this in hydrocarbons that HX when you react with water, sorry, X2 when you react with water, okay, it will form HOX plus HX. And this in this HOX, you will notice that this will be delta negative and this will be delta positive charge. And this delta positive charge is going to be more electrophilic site for benzene. That's why you will see that HOX, which is present as delta positive and delta negative charge. Benzene will attack here more easily. This bond will break. And that's how we can get this as, again, halogen here with H with positive charge and OH minus will come out of it. Okay. And of course, OH minus is a stronger base present in the solution that helps in eliminating this H plus and retaining the aromaticity. So OH minus will take away this H plus, push this bond, and therefore you can get an aromatic ring formation here, right? So this is how the halogenation can be done using uh, halo water. Okay, everybody understood how the halogenation is done? Please check it out once quickly. Right. Okay. So when it comes to nitration, if benzene is treated with concentrated, okay, I'll put it. So if it comes to nitration here, you can see with concentrated HNO3, with concentrated HNO3 and H2SO4, which we call it as a nitrating mixture. With nitrating mixture, you can convert that into nitrobenzene. Alternative nitrating mixtures are concentrated HNO3 with HBF4, N2O5 with HBF4, N2O5 plus with the salt of BF4 minus, N2O5 anhydride, NO2 plus and BF4 minus. These are all the alternative forms of it. In all of these cases, it's pretty clear that it will give you NO2 plus as the electrophile. Okay. So now our objective is to figure out if you get NO2 plus, how does the mechanism takes place here? Okay. So see, we'll do it step by step. The first thing is generating the electrophile, that we do not count it as a step. But see, HONO2, this way, if I write it as HNO3, okay, that when you treat with concentrated H2SO4, which is HOSO3H, like this, then what can I say? That the lone pair on this OH will take H plus and convert itself into H2O, NO2 with a plus charge here, and this will become HSO4 minus. And this H2O, NO2 plus, correct? Here, water is a good leaving group, so water will leave very easily and giving NO2 plus H2O. Now, this is only possible when this will act like an acid and this will act like a base, correct? Which means If it comes to acidic strength, the acid whatever that you are taking, correct? HOX acid whatever that you are taking should be greater than HNO3 acid. Then only nitration is possible. Okay. So in that case, we can get NO2 formation here. And once you get NO2 here, now from NO2 plus, we have to make the reaction. All right. So how will I make it? So first benzene, I'm directly writing the steps now. Everybody look into it. NO2 plus, I'll write the first step as electrophile coming at this position, NO2 with a plus charge here. And second step is once you get NO2 here with a plus charge, then the HSO4 minus, which has hydrogen here, will be removed out, and benzene is been, I mean the aromaticity is being retained, and that's how we can get H2SO4 back and nitrobenzene formation. Okay, this is a typical reaction of nitration on benzene. Throughout the organic chemistry, wherever you see benzene or benzene based compounds like phenol, like aniline, like nitrobenzene, in any case, nitration will have the same mechanism. Okay, in all of this case, mechanism does not change. EAS mechanism is same. Okay, now notice what is the role of concentrated H2SO4 here. Nitration is effectively a slow process in the absence of H2SO4. H2SO4 has no effect on benzene under normal conditions. H2SO4 behaves like acid and HNO3 behaves like a base here. Okay. There is no kinetic isotopic effect observed during nitration. Okay. This is the important crux of nitration, everybody. Please check it out quickly. Done. Next, let's notice sulfonation. You have benzene plus concentrated H2SO4. You can get SO3H with benzene, which you call it as benzene sulfonic acid. The reagents that are typically used in this case are fuming H2SO4, oleum, which is H2SO4 and SO3, concentrated H2SO4 with concentrated HClO4, all of these cases where we can get SO3. Okay. Here mechanism is something which you need to be very careful with. See, how does the mechanism operate here? If you take HOSO3, sorry, SO3H, this is the acidic part of it. And the second mole of uh, second mole of sulfuric acid, I can write it as HOSO3H here, correct? In that case, this O will act like a base extract proton from here. So that makes it H2O with SO3H plus. Okay. And the second part of, I mean, the second mole of HSO3 here will be converting into HSO4 minus. This is the form you will get. And once you get that here, this particular part H2O and SO3H plus, it will lose out water and convert into HSO3 plus. HSO3 plus. And see, HSO3 plus can further react with HSO4 minus because it is still an acidic form. So this can lose an acid and convert into SO3 plus H2SO4. So this SO3 formation here is the electrophile. This is the electrophile. In fact, directly HSO3 plus can also be used as an electrophile. It depends upon quantity. Quantity wise, SO3 is more available. Okay. And now, if you react with benzene here with SO3, we know that first step is all about getting SO3 minus here, H here, plus here, this way. And you see internally hydrogen will transfer onto that to retain the aromaticity, hence converting into SO3H. Clear? Is this case clear, everybody? This is how the mechanism takes place. Okay. Now read in here, H2SO4 is acting like both acid and base here. SO3 is neutral but a good electrophile because of its high oxidation state. Sulfur has plus 6 oxidation state. Both SO3 and HSO3 plus can be treated as electrophile here. Okay. Done. So this is a mechanism for sulfonation, everybody. Clear? Now, on benzene, one of the famous reactions, and we'll be, I mean, this is a very, very frequently asked area in J Advanced or mains, is Friedel-Crafts reactions. Friedel-Crafts reactions are of two kinds. One is alkylation, the other one is acylation. Alkylation is a part where we make an alkyl to substitute on benzene, correct? Where we can say alkyl is getting substituted on benzene here. Okay. But it requires a Lewis acid to do that. In fact, any alkyl substitution on benzene is typically regarded as Friedel-Crafts reactions. Now, the Lewis acids which we typically use are BF3, AlCl3, SnCl2, FeCl3, ZnCl2, all of these in their anhydrous forms. Now, let's put through the mechanism here. So, step by step, if you notice, first RCl, alkyl halide, when you treat with AlCl3, that will convert into, you know, R with Cl and AlCl3, this gaining delta negative charge and this gaining delta positive charge. And whether it becomes a complete carbocation or not, that depends upon the stability of the carbocation. If the R plus can become very stable carbocation, it can immediately break it into R plus. Otherwise, benzene will directly attack on this, transition state, that is R, Cl and AlCl3, which has delta minus and delta plus. So benzene will attack on this R here, and that's how Cl will go away, and you'll get R with hydrogen with plus charge this way and AlCl4 minus. Okay, this is the product that you will get here. And now, once you get this through, we will get this as R and H with a positive charge, and AlCl4 minus will attack back so that it can retain the aromaticity, thus making this into an alkyl group with HCl plus AlCl3. So that's how alkyl gets substituted on benzene. Okay, this is how typically it would happen. Okay, now what you need to notice is like this one, that when it comes to strength of Lewis acid, that which one can act like a stronger Lewis acid, and so you will see that AlCl3 is a stronger Lewis acid as compared to FeCl3, as compared to BF3, correct, as compared to ZnCl2, and as compared to SnCl2. Okay, now in all these cases, I would want you guys to remember it this way, that in this case, no rearrangement, no rearrangement of carbocation takes place. But AlCl3 can definitely, being a strong electro or strong Lewis acid, it can remove the halogen quickly and produce a carbocation. And once you get a carbocation, rearrangement will definitely happen. Okay, that's the idea behind AlCl3. So notice this one, all the rearrangement cases in Fidelkraft's alkylation. If you have this alkyl chloride in the presence of AlCl3 and you're operating at a low temperature, then the benzene can directly attack here, removing chlorine without a complete carbocation formation. Hence, the major product will be the first one, the minor product will be the second one, which is after rearrangement. But if you notice the same case here, in this case, if you are heating it, that means you are providing sufficient temperature. In that case, it will get enough energy to break, and then, sorry, this becomes a minor product here, and this becomes a major product here. See the mechanism in itself, you can see how the rearrangement takes place when you react with AlCl3 here. So primary carbocation is very difficult to make, but in this case, because you are facilitating with heat, it can form more easily, and this carbocation can get rearranged to form, making a 1-2 hydrate shift. It will go from 1 degree position to 2 degree position, and thereafter benzene will react onto the second degree carbocation, ending up getting a isopropyl benzene. Okay, so the IUPAC name is also, you can use this isopropyl benzene. Isopropyl benzene has a common industrial name known as cumene. So this is the preparation of cumene. Clear, everybody? Now you might ask, sir, when do we need to consider low temperature, high temperature, or anything? In exams, it's very simple. If temperature is not mentioned, you assume it is over the room temperature. That means it is going to be with rearrangement in case of AlCl3. If it is specifically mentioned that you are operating at a low temperature, minus 40 degrees, minus 30 degrees, if that thing is mentioned, in that case, you have to take without rearrangement as the major product. Okay. See the second reaction. Suppose if it is mentioned room temperature, RT means room temperature. That means you know that if it is room temperature, you have to go along with the carbocation formation, which means in the first case, you will notice that this way you have chlorine, sorry, this way you have chlorine. So carbocation will first form here, then 1-2 hydrate shift will take place, and carbocation will move here. So from 1 degree position, it goes towards through 3 degree position. Hence, while writing the major product, you know that this will be the major product here. This is major, and then benzene with this form is minor. Okay, this is the minor product. While if you react this with SnCl2, if you react that with SnCl2, SnCl2 being a very weak acid, weak Lewis acid, here making a complete carbocation is very difficult. Okay. Since the carbocation formation is difficult, now you would notice that these two, sorry, let me just copy that from the above in here. This is going to be the minor product. In fact, it is hardly formed, and this is going to be the major product in this case. Okay, without rearrangement. Clear? Everybody understood? Second is an interesting case. I took BF3 here, but there are two halogens. Now it becomes difficult to figure out which one can give, uh, where do we put the positive charge so that the benzene can attack? See, now this is the way you need to check. If you compare here, you have fluorine and chlorine. Here it is delta plus, delta minus. Here also it is delta plus and delta minus. And BF3 is approached. Now, fluorine has relatively more negative charge than chlorine. Reason being, the polarity will be much more here due to the strong electronegative differences. Because of which, even if the BF3 comes here, this attack is weak. This is a weak attack, while this is a strong attack. You know that F minus is a stronger base than Cl minus? That's the reference. Because F minus is a stronger base than Cl minus. That attack of lone pair is faster, and that will help in breaking this bond more easily. Hence, you will see that carbocation formation on this end with fluorine going away is more often observed, and hence benzene will attack on this position. Therefore, the product what you will get in this case will be like this with chlorine here. Huh? So this is a major product, everybody. Okay. So let me put this as a reason. The reason is, okay, F minus is a stronger base than Cl minus base wise. Okay. And CF polarity is better than CCl polarity. These two are the important reasons. Therefore, if it comes to rate of reaction, okay, then RF will definitely make a better reaction than RCl, then RBr, then RI. Okay. Usually we notice that the iodides are more reactive for substitutions, but in Friedel-Crafts it's the opposite way. RF is a better reaction for substitution here. Right? Everyone, please go through these cases quickly. Please check the rearrangement cases. If there is any doubt, you can ask me now. Check this out. Is there always have to have alkyl halide? Not necessarily. Even if you have an alkene, still we can get this carbocation formation and reaction can happen. In this case, for instance, we can get the product like this. Tert butyl. This is tert butyl benzene. This is tert butyl benzene. Okay. Which means basically if you have a pi bond here, the pi bond will attach on H plus here and thereby giving a carbocation at this position. And once you get a carbocation, benzene will react on that position, positive charge, like this, and it will attack to get this form here. That's it. This is the mechanism that will happen. Now, for this to happen, you should not have some other nucleophile. For example, if I take HCl, what happens with the problem of HCl? I'll tell you. You with first H plus in the form of HCl, if you notice, then first carbocation will form, and then Cl minus will attack. Cl minus will attack, and therefore you will see Cl will come here. Matlab, before even benzene attacks, right? Chlorine will attack. The problem है ना? So we don't want chloride to attack, isn't it? Which means you want to suppress the nucleophilic nature of this halogen, and that is possible when its quantity is very less. मतलब chlorine का quantity ही बहुत कम है. Correct? When is that possible? When you're operating at low temperature and something like HF is there or H3PO4 is there, because they are weak acids, their minus form like F minus or PO4 3 minus forms are very less in quantity. That's why they do not act like a nucleophile. They will help the benzene to act like a nucleophile. That's why you can't take HCl in these kind of reactions. We have to take HF at 0 degrees, H3PO4 at 0 degrees, or PPA means polyphosphoric acids at 0 degrees. In such case, we can get uh, benzene to act like a nucleophile and attack. Okay? Done. Now, Other alternative is instead of alkene, we can take alcohols also. Now, how does the alcohol help? Same logic. You will get OH to get protonated. You will get this as OH2 plus. And OH2 plus can be easily relieved to get positive charge here plus H2O. Now listen up again. Because I am using HF at 0 degrees, you will not have sufficient fluoride ion to attack here. And that's the reason why benzene has the leverage to attack the carbocation here now. And therefore, you end up getting the product as cumene here. Correct? So this is another alternative method of making an alkyl substitution. Okay. Sir, is it the only way? No. Even if you take alcohol with BF3 also, any Lewis acid, still the reaction is same. The lone pair will attach here. You will get this as OH and BF3 with minus and plus charge here. This becomes a good leaving group. Oxygen will leave, gets a positive charge. We will get this as BF3OH. And once you get a carbocation here, this carbocation will indulge with the reaction, indulge with a electrophilic aromatic substitution with benzene, ending up isopropyl benzene or cumene. Everybody clear? So if you have alcohols, we can use either an Lewis acid or simply HF or H plus, simple H plus reaction. The same logic works even in the case of epoxides. So if you have an epoxide and you react this with AlCl3, a Lewis acid, lone pair from here will attack and converts this into O with AlCl3 minus and plus. This is an electrophilic part. So benzene will attack on that position like this with AlCl3 minus and plus. As benzene attacks here, the bond will break onto this side. So we will get benzene with this form having an H here, positive charge here, double bond here with Al, sorry, one more carbon should be there with oxygen and Al, Cl3 with minus. Sorry, can we put like that? Can we put a harmony line? Sorry, once we get this, oxygen will take this minus charge from AlCl3 and pull away this H plus, retain the aromaticity, and then we can have this as OH plus AlCl3. So that's how the final product will be this ethyl alcohol. This is ethyl alcohol with a phenyl substitution. Ethyl alcohol with phenyl substitution. Correct? The same mechanism happens even in the last case here. So you can see oxygen with AlCl3 with plus charge. We have two methyl groups here this way and with minus here. And when benzene attacks on this position here this way with O, AlCl3 minus and plus. See, benzene will always attack on the more substituted position. It will attack on more substituted position because their bond breaking is easy. You could imagine like this, at that position, the carbocation is more stable. Hence, final product what you will get here is there are two methyl groups connected to one more methyl with OH group and AlCl3. This is the final product. So this is the same product which you can write down here as well. Okay. So quickly go through these mechanisms, everybody. Check out all these four cases. If you find any problem, you can ask me. If you guys have understood that, please try these two cases. Please try these two cases. How do we get and what is the answer? So the mechanism goes like this. First, we have benzene here, and on this position, H plus will get added, positive charge will come. And this positive charge is already at a stable position. We have a 3-degree position. So 1, 2, 3, 4, 5. So 5 position if you have. Okay. So if you get attached here, so you'll get a methyl here. 2 methyl groups will be present here like this. Because the attack now would happen from this side. So this is the final product what you will get. Clear? Second case. If you get a positive charge here, this is at a 1-degree position. 1-degree position is not stable. So 1, 2 methyl shift will take place. So as the methyl shift happens, this is how you get a positive charge now. And that's where the benzene will attach on it. So you will get like this with methyl and this one. Okay. So this is the product formation. Then this case, this is the product formation. Clear? Next, let's understand what is Friedel-Crafts acylation.
तो
हाँ बेटा.
ये वाला एक्स्ट्रा कार्बन जो आते हैं ऐसे
Mm-hmm.
ये वाला एक्स्ट्रा कार्बन है the
You mean in
product
the fifth one?
yes sir, the first one the product
The fifth one, how many we have here now? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 carbons only, no? But
chlorine no
chlorine is lost. So we have
carbon
1, 2, 3, 4, 5 carbons.
sorry that's my mistake sorry
Huh?
it was my mistake it was my mistake
अच्छा, ठीक है. Clear? Right, next. Let's see about Friedel-Crafts acylation. Here we have acyl chloride here. That when you react with some Lewis acid, let's say AlCl3. So first thing, here a complete carbocation will form, beta, irrespective of whatever the Lewis acid is. कोई भी Lewis acid हो, ऐसा क्यों हो रहा है? Reason being, this carbocation is very very stable, okay, because the positive charge on oxygen can be resonance stabilized by the oxygen here, thus giving a triple bond formation. You think this way, इस कार्बन के पास there was only 6 valence electrons, now it has 8 valence electrons, so that means it is an octet completed carbocation case. And you know that octet completed carbocation cases are very very stable form. That's why irrespective of whatever Lewis acid is, you will always create this carbocation form. And this carbocation formation is called as acylium carbocation. Acylium carbocation. Acyl is a C double bond O bond. So after C double bond O, this bond is called acyl. Acyl breakage, acyl cleavage. Okay. So on that acyl position, we are getting a carbocation. And then benzene reacts on that carbon. So we'll get RC triple bond O with a plus charge here. So benzene will attack on this. This oxygen will move, and thus we will get a double bond carbon with an R group here. Okay. So what we are getting here is an alkyl and benzyl ketone. Alkyl benzyl ketone. Okay. Of course, because the stability is much more in the acyl position only, no rearrangement further will take place here. So this is Friedel-Crafts acylation, everybody. Okay. Now notice, in an alkylation, chances of rearrangement product will be formed. In acylation, there is no rearrangement. In both cases, it is a drawback with each other. Okay. For example, you're expecting that there should not be, so there should be some rearrangement, but acylation does not give that rearrangement possible. Okay. Now notice here, a polyalkylation is possible in the case of Friedel-Crafts alkylation. That is, if you take CH3Cl in the presence of AlCl3 here, you can get methyl benzene and CH3Cl first. But notice, if you have CH3Cl in sufficient quantity, now if you raise between methyl and toluene, that means between these two, toluene will have much more faster EAS reactions. So therefore, toluene will react and toluene will give you multiple products here. That is CH3 with alkylation happening at ortho position, alkylation happening at meta position, and alkylation happening at para position this way. So you will get this multiple product, right? So this poly substitutions will happen. And will they stop here? No. Depending upon excess, it will keep on happening further. So you'll have CH3, CH3, and it can become CH3 here like this. See, eventually what happens, thermodynamic, because these methyls are very, very close to each other, they will keep rearranging on benzene, and eventually the product what is formed is this one, which is mesitylene. Mesitylene is the most stable product. If you do polyalkylation, mesitylene is most stable product. Here also it will form mesitylene. Okay, that's why everything will get rearranged into the formation of mesitylene. So you can see chances of how many products you are getting. Benzene से start किया आपने, ये product मिलेगा, ये चार product यहाँ मिल गए, पांच ये मिलेगा, rearrange होके छह ये मिलेगा. Okay, इतने सारे products मिलना start हो जाएगा. This is a drawback of Friedel-Crafts alkylation. जब भी आप alkylation करते हो, chances of multiple product formation is observed. Next, acylation. In the case of acylation, expectation is that when you have an acylation, C double bond O Cl, in the presence of AlCl3, you are expecting the product as like this, C double bond O this way, plus AlCl3 plus HCl, barabar. But what is the problem that happens is, in this acyl carbocation, this is the acyl carbocation form, when the adjacent carbon of acyl carbocation is extremely stable, you will notice that a positive charge will be shifted in, carbon monoxide gas will form and release. Now, this type of formation is only possible when this carbocation is very stable carbocation. Very stable carbocation. And because of stable carbocation, now instead of acylation, alkylation is more favorable. So you will end up getting this as a major product. Tert butyl benzene as the major product. हम लोग को लग रहा है कि acyl benzyl major product होना चाहिए, but this will become the major product. So this is also a drawback. Okay. And that's why what you do to avoid these two situations, right? एक तो हमको alkylation में problem नहीं होना चाहिए, acylation में भी problem नहीं होना चाहिए. In that case, the first step you always do is acylation. You do acylation here. So you will get this as C double bond O R, correct? And now you know that C double bond O R is a withdrawing group on benzene, right? Because by resonance it will try to pull the electrons out. So in that case, between benzene and acyl benzene, you will notice that the benzene is more reactive. So ये further acylation नहीं होगा. So this step is avoided. Further acylation does not happen. And if you want to convert this acyl form into alkyl form, it's very easy. We can use Clemmensen's reduction or Wolff-Kishner reduction, where they convert any form of ketonic or aldehyde groups into alkane. So now the final product is alkyl product, alkylation product. So don't do directly alkylation. Instead, you make an acylation, then reduce it. This way, both the problems are avoided. Okay, clear? So this is an important note for Friedel-Crafts reactions. All the Friedel-Crafts reactions where we want a particular type of alkyl group, we always use this type of mechanism. Okay, next. Notice which groups will actually give Friedel-Crafts reactions, right? So we need to figure out which group will actually give Friedel-Crafts reactions. See, benzene definitely gives, methyl benzene will give, ethyl benzene will give, isopropyl will give, tert butyl will give, any halobenzene will give positive value, nitrosobenzene will give, OCH3 will give but to a less extent, CH2Cl will give, double bonded carbon present on benzene will give Friedel-Crafts reactions, phenolic group will give but to a very poor extent. Okay, now this is little strange to understand because this is a very strongly donating group, which is a very strongly donating group, yet it is not facilitating the Friedel-Crafts reactions. Okay, which means group where Friedel-Crafts reactions are not observed is either they are very strongly donating or very strongly withdrawing. There should not be donating also, they should not be very strongly withdrawing also. Now, which are those groups? How do we identify them? See, these are the groups which are very strongly donating on benzene. Any directly connected nitrogen with a lone pair, Nr2, NHR, NH2, and same goes with OH, O minus, NH minus. These are all very strongly donating groups. While strongly withdrawing groups like NO2, cyanide, CHO, COR, COCl, COOH, SO3H, anything which has a plus charge, or for that matter, anything which has CX3. Okay, X could be fluorine, chlorine, bromine, anything. These are all very strongly withdrawing groups. So if we are strongly withdrawing or strongly donating, in both cases, Friedel-Crafts fails to give the reactions. Now notice in the case of phenol, we are expecting that the benzene will attack on Rx, where X will attack AlCl3. Alternatively, what happens? The lone pair present on OH will also attack the Lewis acid, and once oxygen gets a positive charge, this entire group becomes strongly withdrawing group. Because of its strongly withdrawing group, this attack is nullified. That's why we say it is going to give you poor yield of product. But in the case of NH2, the withdrawing is so effective, so strong, there is no product only. So if you react with RX, no reaction. At least in phenol, there is some product, but here there is no reaction at all. Okay. Like NO2 in this case, NO2 is very strongly withdrawing anyway. So that will not lead any kind of alkyl halide reaction. So in this case also no reaction. So you can notice that electron withdrawing group decreases electron density on benzene, so no ES reactions are observed. Electron donating groups will increase the reactivity with electrophile. Okay, but problem is with Lewis acid, they also become electron withdrawing groups. Correct. So I want you to first go through these statements carefully, understand which case Friedel-Crafts will happen, and why they will not happen. Okay, later we can go to the next part.